Okay, any questions before we get started? Okay, so we left off last time talking about transforming an alcohol into a chloride, bromide, or sulfonate ester. And then now that you have a good leaving group, you can attack it with any nucleophile to make any other functional group. And then there's this table that lists common nucleophiles, the solvents you do for, the SN2 reaction, where you'd expect to see IR, absorptions, what mass spec would tell you in carbon-13. So we're going to continue on with one aspect of that, primarily ethers. So every textbook has alcohols and ethers in one chapter. And ethers are like the paint on that wall, just very boring. So there's not too much exciting that's going to happen in the first part of the lecture here. Not that that'll be any different from any other lecture, but I think once we get to the amines, that's a little bit more exciting. The structures are more interesting. A common name reaction for organic chemistry is the Williamson ether synthesis. And so we're making an ether. And so that has the carbon-oxygen-carbon bond. So it's a pretty classical reaction. And what I want to point out to you is when you look at an ether, you have the two carbon atoms bonded to the oxygen. And so if we're looking at this product, 2-methoxy, 2-methylpropane, we can see that the one carbon is primary and the other carbon is tertiary. So if we're thinking in terms of an SN2 reaction, that would necessitate that we have to start with an electrophile that obeys the SN2 kinetics. So remember, that was methyl was greater than primary, greater than secondary, and tertiaries do not react by SN2. So that's why we're using the least substituted carbon as the electrophile. The most substituted carbon, the tertiary, that's going to come from an alcohol. So under these conditions, we're using tert-butanol is the nucleophile and the solvent. And then our base is potassium hydroxide. So what that's going to form is potassium tert-butoxide. That then does the SN2 reaction. And so we end up with an ether. So again, the oxygen is saturated. It has 2 sigma bonds, 2 lone pairs. Ethers in general, they make good solvents for other reactions because there's a little bit of polarity due to the CO bonds, and essentially they do not have an acidic hydrogen, so they're inert. So I don't know if you've used, this always looks like a bat out of Legend of Zelda. So diethyl ether. So diethyl ether is a common solvent. I don't know if you've used it in lab. It smells really nice. So when I'm feeling down, I open the can and take a deep breath. It gives me joy, for momentary joy, I would say. So ethers, they have lower boiling points because they don't have the OH. So they can't hydrogen bond, so they're more volatile and they smell a little bit more. They tend to smell pleasant. When we look at the amines later today, amines do not smell pleasant. They smell very musky or fishy. So they're unpleasant. Here's a nomenclature table looking at primarily a symmetric pattern. So if your eyeball is on the oxygen and then you look at the carbon groups bonded to that, if both of those groups are the same, then the ether is symmetric. So you can just look at the carbon count. You see they're increasing by even numbers here. So dimethyl ether, you see that boiling point's pretty low. So it's a gas at room temperature. When you get up to diethyl ether, now that's a low boiling liquid, so 34. It's probably one of the most common organic solvents to extract with. Since it's low boiling, you can then distill it off easier. When you get up into these higher chain ones, the boiling point's higher. So you can use them to like reflux reactions in and things. And then the big one up here, diphenyl ether. I've used that a couple of times. This smells bad. So that's not pleasant at all, but it's now, you got some aromatic rings and an ether, so it has other things you can do with it in terms of like non-covalent interactions to help transition states. But like I said, they're symmetric, they're the same. There's not much more I can say about it. One thing to note though is when we look at this table, say like this group here, and I need the same molecular weight, so that group there. What you'll notice is like the first one in each is linear, and then the second one is branched. So they have the same, each pair has the same molecular weight, but you're going from linear to branched. And basically the trend is that the linear has a higher boiling point, and then when you branch it, it decreases. And so that's the spaghetti argument. Spaghetti, if I can spell it. And then branched is the M&M argument. So when you cook spaghetti, it gets all entangled. And so that's how the linear chains kind of look. So it takes more heat to untangle those chains. And when it's branched, it's more spherical like M&Ms. So they're only sort of the surfaces of those spheres are touching. So it's easier to boil them when you have branched chains. And again, as a practitioner, you would look at, okay, how do I want to remove this solvent ultimately from my reaction? And you want something as low as possible so you're not spending your 8-hour workday removing solvent from a reaction. So non-symmetric ethers, basically each side chain is different. And so you name them according to the longest chain. So this first one, you have a two carbon chain and a 1 carbon chain. And so the parent gets the longest chain, and then the shortest chain you just shove oxy after it, so methoxyethane. Some of these, you can see the next one is 1-methoxypropane, so you have to specify where that substituent is on the parent. So what would the isomer of that be? So that would be like 2-methoxypropane. So those were linear ones. You can have branching off the side chains, and then you can have cyclic ethers, cyclic side chains. So any questions? Again, it's very vanilla. It's not terribly exciting chemistry.
So the cyclic ones will have lower boiling points or higher?
The what?
The cyclic ones?
I would assume to a certain point they'd probably be lower, but then a little bit you're combating the more carbons in that ring that can affect it as well. So once you get sort of past 5 and you're 5, 6, 7, then it would probably be a little higher. Cyclic ethers are maybe a little bit more interesting. We'll see review epoxides, so that's the 3-membered ring. Oxytanes are the 4-membered ring. Tetrahydrofuran is a common solvent. That's a 5-membered ring. Tetrahydropyrans are 6. So maybe what I can say is 5 and 6 are scaffolds for sugars, carbohydrates. So what does DNA stand for? So the sugar in that it's a 5-membered ring. And so your normal sort of sugars like glucose are 6-membered rings. And depending on the chain length and how the alcohols sort of bite back on one another, you can get 5 or 6-membered rings. So we'll talk about that in Module 5 of this semester. 7-membered rings and 8-membered rings, oxapanes and oxocanes, are probably less common, like synthetically, but they're found in a lot of marine natural products. So if you like scuba diving and whatnot, what is it? It's February, so probably a little late in telling you this, but the REU programs for the summer have probably closed by now, but there's these research institutes where you can apply for summer research experiences. And there's oceanography institutes and these some research projects. You go on a boat in your scuba gear, you go down and collect like sponges and whatnot, and then you extract out like unique compounds. And particularly in the marine environment, like 7 and 8-membered rings are pretty common. So maybe I'll post a discussion on Canvas about some of those structures. So as I said, ethers are there's not much about them spectroscopically that's a nice diagnostic signature. That's why everything is in yellow here. So when you're looking at IR, you have an alcohol if you have that OH group. You have a carbonyl if there's that strong signal around 1700. Ethers don't really have anything that is going to indicate to you this is an ether. So you kind of have to do indirect logic in thinking about it. If you're lucky, you might see something in the fingerprint region, but again, we ignore that. Proton and carbon are a little bit more helpful because then you start seeing signals that are past your normal sort of CH or C for sp3 hybridized carbon. When they're in these regions 3 to 5 or 40 to 70, that's indicating to you that the carbon atom has some heteroatom on it. And then you can use if the mass spec was odd, you could say, well, it's nitrogen. But if it's even, then you could say maybe there's an oxygen. So it's still a little bit ambiguous about ultimately assigning if there's an ether oxygen in there. So since the IR is nothing special, I don't have one to show you. A little bit about the impact of the ether on physical properties. So as we said, that oxygen has 2 lone pairs. So the bond is polarized. So you do get some polarity. And because of the lone pairs, it's a hydrogen bond acceptor. So if you had, say, a low molecular weight ether, something without a lot of carbons, then you would expect to see some miscibility in water. It's not going to completely form one phase, but you'll get a percent of that ether that will go into an aqueous phase due to that non-covalent interaction. So this H bonding. And as I said, for any molecular formula where you can make an alcohol or an ether, the ether will always have a lower boiling point. And we saw hydride reductions, so like lithium aluminum hydride. That's typically run in THF, so that's tetrahydrofuran. So it supplies enough polarity to help get things dissolved and help it through the transition states and whatnot. But it's not a solvent with an acidic proton that would quench the hydride. And the last statement, is just showing you common solvents that we would use in lab. And the choice of these is really on cost. So diethyl ether is the cheapest, so that's used the most. Questions? So we saw a reaction to make an ether already, but what's the strategy that we want to think about if we're given, this product with an ether? How do we want to think about the 2 different CO bonds? And in this example of 1-ethoxy, 1-methyl cyclohexane, we have the 2 carbon atoms bonded to oxygen. So really what you're doing is classifying them as alcohols. So one of them would be primary, the other would be tertiary. The one that's more substituted is the one you want to leave with the oxygen, so it can come from an alcohol that you can make an alkoxide from. So that alcohol plus a base makes the alkoxide, that's the nucleophile. And then the least substituted one ends up being a good electrophile. So this would be, I'll draw it in green here to match that would be making that bond. So you wouldn't want to do it the other way because you end up with a tertiary alkyl halide, and that's no good for SN2. And again, if it was a symmetric ether, then you don't really have a problem. You make sort of one side your alcohol, and then the same carbon count, you have to have a leaving group on. This is a cheap example of the prior slide. So we do the same thing. That carbon would be secondary. That one would be tertiary. And so we could say this should come from a good electrophile. And then this tertiary alcohol. Any questions? So it's like running on a treadmill, right? It gets boring after a while. So one specific class of ethers that's important are epoxides, because the three-membered ring is strained, and then we can take advantage of that strain release reactivity. And we can do it in two ways, as we learned, either under acidic or basic conditions. So epoxidation of alkenes, you'll find more of this from your 255 notes at the end of the semester there. We finished up on this. So an alkene we can think of as a nucleophile, and then this reagent MCPBA, which stands for 3-chloro, man, this is a weird name. I'm going to cross that out. So meta-chloroperoxy benzoic acid. So MCPBA. What it does is has this peroxide bond. So a peroxide is an OO bond. And that blue oxygen is electrophilic. So what it does is a 1-2 addition of the alkene, where both carbons now are bonded to that oxygen. And so the name says 2-ethyl-oxirane. So epoxides, oxiranes are the same thing. So that has strain, and we can use that strain to release it either through acidic conditions or basic conditions. So stated another way, anytime you see an epoxide, you know that it can start these two carbons they can come from an alkene. Any questions? So this arrow just means we're thinking in reverse. So if you have a product that has an epoxide in it, if you want to get back to simpler and simpler things, you can start from an alkene. So the alkene treated with MCPBA makes the epoxide. Yep.
You said it can come from an alkene. Does that mean it comes from something else too? It can come from something else?
MCPBA is the easiest thing. this other comment down here. Another thing we learned, if you take bromine and water, that's going to form this thing called a halohydrin. And so now that is set up to do what I'll call an SN2 reaction, but it's really not two because everything's in the same molecule. So you have a good leaving group here. Then you have an acidic proton here. So from that, you can treat with a base, which deprotonates the oxygen, and that forms a nucleophile. Then you have this leaving group right next door, and so it just ring closes. So this would be like sodium hydride in THF. So either method is plausible. So I'm going to cross that out because this is not iClicker. So HA, what should that look like in the proton NMR? What now? It's close. So the question is really getting at, you see this carbon, you would say to a first approximation it has two hydrogens. But they're labeled A and B for a reason, because HA has a different relationship to HC than HB does to HC. So those two hydrogens, even though they're on the same carbon, that's called geminal, they're not equivalent. So that and that are different. So those atoms here, I didn't draw it, but that should be sort of projected out towards you. So 1, 2, 3, 4. Those groups all lay in a plane. And then you look at the dihedral angle of that. So HA, HC is what dihedral angle? Anybody? So it's 180. So if you can imagine taking HA, and then you gotta, I can't move my arm all the way that way, but like, you have to rotate it all the way that way to get to HC. So HB to HC is what dihedral angle? So they're like right in front of each other, so that angle is 0. So because they both have different relationships to C, they have to be different. So A couples to C because it's a neighbor, so that's a doublet. But since B is different, it also couples to that, even though they're on the same hydrogen. So what you end up with is a doublet of doublets. The coupling from A to C is probably like 13 hertz or something. But then A to B, since the angle between them is smaller, it's probably like 2 hertz.
You mentioned that the C should be towards us.
Yeah.
Okay.
So the long story short of this is that ring locks those atoms in place. Stated another way, this bond right here does not rotate. And so if it's locked in place, there's no rotation, the angular relationships change. So what about C? You have the right term. Can you put it, sort of expand it in the right order? So we know HA and HC couple. So that's a doublet. HC and HB couple differently. That's a doublet. Then you have these. That's 2, so that's a triplet. So you get a doublet of triplets. So I think maybe next spring, if you're interested in more of that, I think it's CHE404. That's where you learn to analyze things like that. It is fun, trust me. The way you analyze it, you draw tree diagrams, and then you're able to, even though the signals look complex, you reduce the complexity through these trees. And it's a nice logic problem. So that's just a review of, once you lock something in place and you set those angles, you remove symmetry that you might think would be present. Questions? So I think I have 2 more slides. So I'm just going to briefly show you that reactivity profile of epoxides so you can understand why acidic versus basic media is different. So acidic media. The first thing we'll do is let's classify each carbon of the ether as an alcohol. So the terminal carbon, if you were considering that bonded to OH, how would you classify that as an alcohol? So this would be primary. And then the other one would be what? Secondary. So if we're in acidic medium, that means that the epoxide oxygen is going to be a base. So say we're treating that with hydronium. So we do a proton transfer. And now that oxygen gets positively charged. We said that the epoxide ring is strained, so it wants to open up. And the reason that you're classifying those carbons is because it's gonna open up to the more stable carbocation. So in this case, it would break that bond. And then give you a secondary carbocation. If we're in basic media, and what I mean by that is, say, like a strong nucleophile. We can do the same thing. It's still primary and secondary. But now we want to treat with, say, potassium cyanide and DMF as a solvent. So like an SN2-like reaction. So now it's going to go the opposite way. The nucleophile wants to attack the least substituted carbon. I say SN2, but the leaving group doesn't leave the molecule. That carbon is still bearing the oxygen. But the mechanistic reasoning holds the same in that the nucleophile attacks the least substituted carbon. So again, as you're reasoning your way through problems, at this point you want to start thinking outside of memorization of things and understand the reactivity profile of the reagents that are involved. So nucleophile, electrophile, oxidant, reductant. One more ether reaction, and that's the cleavage of ethers. And I've given you sort of a rigged case here. So we have ethoxybenzene. We're going to treat that with HBr. So HBr is an acid, so the ether has to be basic. So let's protonate it. So you have that oxonium, then you have bromide, and I'm showing you the products. If every ether has 2 carbon atoms, why are we getting the products listed? So I'll call that blue. Call this one green. The mechanism is going to proceed by SN2. So what's the difference between the blue and the green hybridizations? So blue is sp2 and green is sp3. So if it's going by SN2 reaction, we already know that sp2 hybridized carbons do not undergo SN2 reaction. So bromide will be the nucleophile. It'll attack that specific carbon. If both carbon atoms were sp3 hybridized, you would just then analyze them according to the class, primary, secondary, tertiary. And that would give you guidance on which one gets attacked. So in a way, this reaction itself is called a deprotection, because what we've done is unmasked the alcohol. And so, again, we would do that if we wanted to do like a Grignard reagent in some other part of the molecule, so we don't have an acidic proton present. So I think, how many people actually bought like the ACS study guide? So a fair amount. I think I ripped this problem right out of there. So it's one of the study guide problems, but it demonstrates a lot of concepts that we've learned. 3 more. And we're going to finish off with thiols. Thiols are the sulfur variant of alcohols. Thiols and thioethers, the chemistry is similar in the sense that, going down the group, so this group here, sulfur is below oxygen. So instead of calling it an alcohol, it's a thiol. And what's interesting is, you can drink, how much water can you drink a day before you would die? Does anyone know? It's not an infinite amount. I mean, at some point your electrolytes get diluted and your heart would stop. But so you can drink a lot of water, right? Like H2S, like that will like kill you instantly, right? Because it's a poison. So just the size of oxygen versus sulfur, it's amazing the stark differences between those two molecules. So for whatever reason that I have not bothered to look up, things containing sulfur like really smell like bad, like farts kind of. If you go further down below sulfur, there's selenium. And so if you imagine the trends continuing, if you ever smell the sulfur compound, it's off-putting, right? Now imagine what selenium does. It will physically make you gag. It's very unpleasant. So one of these is used, gotta think here. One of them's used in natural gas, right? I can't remember which one. But like if you have like a gas stove or gas heat in your house, it's sort of doped with a little bit of that. So if there's a leak, you can sort of smell it. Not much, but so it's the nomenclature, just stick thiol at the end. Bada bing, bada boom. Same thing, you can treat a thiol with a base, then an electrophile to make a thioether. And sulfur is interesting, again, because it's in a different period. And what it can do is then form other oxidation states that oxygen cannot. We might see a little bit of that. Next week's your spring break, right? So we come back, then you have Monday, and then I think your exam. So I think on that Monday, I'll show you sulfur at a different oxidation state. Or I guess we already saw it, right, with the, what was it, like CH3OS. So like that sulfonate, you see the sulfur is at like a higher oxidation state. So oxygen could never attain that, just because in that next period there, now those elements have access to d orbitals. Any questions? All right, we made it through. Now something, what I find a little bit more exciting. So amines, again, we're still in oxidation state 1 of carbon. So now these are carbon atoms bearing a sigma bond to nitrogen. And so amines have 4 classes. And so what you're doing is looking at the nitrogen atom and then just counting the bonds to carbon. So a primary amine would have 1 bond to carbon, secondary 2, tertiary 3, and then 4 is called quaternary. And then notice it has this positive charge. So why is that? Because that lone pair that was present in primary, secondary, or tertiary is now taken up by a 4th substituent. The easiest way to name these is just shove the word amine at the end and stick the carbon substituent in front. So methylamine. Any Breaking Bad watchers in the crowd? No one wants to? Okay, so hopefully you know what I'm talking about. So one of the best episodes in that series is they're hijacking like a train with a tanker car full of methylamine. So that gives you the volume, idea of the volume they need to do their illicit synthesis. And there's the next scene in there is just, your jaw will drop. It's pretty wild. So it's a low molecular weight amine. Notice the boiling point. It's typically sold as a solution in water because you do have hydrogen bond donor acceptor now, so it's miscible with water. And then as you start substituting more carbons, you go to secondary, tertiary, and then you just shove the di or tri in front of it. Probably the most common base that we use in lab is this tertiary one called triethylamine. So it's a nice base. And so by that word base, we mean it's abstracting a hydrogen. So when it does that, so for example, triethylamine with HCl, now you form a salt, so triethylammonium chloride. So we'll come back to that concept. Amines are good bases. So you know of like sodium hydroxide, sodium bicarbonate. Those are inorganic. So obviously they're not soluble in organic solvents. So the amines, since they have that lone pair, they're basic, and therefore they're soluble in organic solvents. You run the reaction, you get one phase. You don't have a heterogeneous mixture or something like that. So nitrogen will have 3 sigma bonds, and then the lone pair is, really what makes it a special element. So that's indicated here. That's the lone pair by that little lobe. And in one sense, you can think of that lobe as the 4th substituent. Even though when we're doing like CHE rules for R and S, we never consider a lone pair a substituent. If it was, it would be the lowest priority. But that lone pair forces the 3 other substituents into the trigonal pyramidal geometry. So like in ammonia, the hydrogens are not in the same plane as the nitrogen. What the lone pair is doing is forcing them into another plane. And so through that, if you draw this like triangle, and then you connect it like that, that's your pyramid. Let me put out a plug for Andy Math on YouTube. So this dude is amazing. I watch these videos at night when I'm trying to fall asleep. He does like algebra and geometry problems from like high school. If you had this guy as a high school teacher, you'd be a mathematician. I mean, he'll take a problem that looks complex and solve it in like 3 minutes using these simple relationships with like geometry and stuff. And it's intellectually satisfying to watch someone solve a problem in like 3 minutes. It's pretty wild. So as you see, when you start substituting the H's for methyl groups, then you increase the class, and then you get up to the salt. So I'm calling that a salt just because you have a cation and an anion. And the reason I mentioned the lone pair like being a fourth substituent, because of that sort of triangle, that trigonal bipyramidal structure, it almost looks tetrahedral, like sp3 hybridized carbon. And so if the lone pair is considered like a fourth substituent, if you have 4 unique things, then you can get R and S. But the issue is that lone pair sort of inverts from one side of the pyramid to the other. And this is called a Walden inversion. It's like when it's raining and it's windy and you have your umbrella, and the umbrella is this way, like having the rain run off and not collect. And then a gust of wind happens, and then it inverts. And now it's like a cup, and it's like collecting the water, and you don't want it to do that. So that's what the nitrogen is doing. The substituents go from one side to the other. It happens really fast at room temperature, so you don't really see that they're enantiomeric. But if you have big enough groups on the nitrogen, if they're sterically bulky, then you can sort of freeze out one enantiomer over the other. So that's maybe for this class an intellectual curiosity, but a lot of people study this stuff research-wise. So we saw cyclic ethers, so with oxygen we can have cyclic amines. So the 3-membered ring is called aziridine. 4-membered ring is azetidine. 5 is pyrrolidine. 6 is piperidine. 7 is azepane, and 8 is oxocane. In terms of the module 5 biomolecules, carbohydrates and DNA and those things, those use oxygen heterocycles. I can't really think of anything we'll learn where we're using these type of nitrogen heterocycles that are saturated, like the carbon atoms are saturated. We'll look at other nitrogen containing heterocycles that are aromatic. So these are non-aromatic. Like in DNA, you have the nitrogen bases, nucleotides. Those are aromatic heterocycles that form the rungs of the DNA ladder through hydrogen bonding. But nothing that I can think of uses like saturated carbon nitrogen heterocycles. Thing to point out as well, all of these must be at least secondary amines because the nitrogen has, to be in a ring, it has at least 2 carbons. And then whether this is H or not, if it's another carbon, then it's tertiary. So the amine group NH2, you can bond it to a benzene ring, and that compound is called aniline. And then you can substitute off for that. The nomenclature changes a little bit in terms of how they're named, but if we considered this primary, secondary, tertiary, that kind of doesn't change. And these have really, really high boiling points. So the nitrogen, if it's NH2 or NH, can be hydrogen bond donor or acceptor. The tertiary can only be an acceptor. And we saw from Module 1 that the amino group is electron donating in electrophilic aromatic substitution, so these are ortho-para directors. And so that was ortho, and the 4 position was para. Just to point out again, see the nitrogen? It's bonded to a ring. So now in this case, we can stick it into a ring. And so these are aromatic heterocycles. So they obey the Huckel's rule, the Frost rule, all of that stuff. But now the nitrogen is in the ring. So the 4-membered ring is called pyrrole. The 5-membered ring is pyridine. This sort of dibenzene ring is quinoline, and then if you shove the nitrogen over one, it's isoquinoline. What is, I'll draw a line here. So the pyridine, quinoline, isoquinoline, the nitrogen all has sort of the same bonding pattern, right? But the pyrrole it looks different. So you can tell by looking at that, the nitrogen's sp2 hybridized. When you look at this one, what does it look like? It looks like it's sp3, but it's also actually sp2. So we know it has to be sp2 because we already learned it's aromatic. And the reason that it's sp2 is because the lone pair has to be in conjugation with these pi bonds. And so we'll talk about the difference between what I'm going to call like a pyrrole type nitrogen versus a pyridine type nitrogen. Those different types are what's important in those DNA nucleotides that makes them hydrogen bond to one another. Questions? So again, primary and secondary can be both donors and acceptors for hydrogen bonding. So a donor just means it has NH. The acceptor means it has a lone pair. The tertiary amines can only be acceptors. And so the hydrogen bond, as a review, this NCI, is an important non-covalent interaction. It's weak, but in general, there's a lot of them. So overall, they add up to something important. Due to low molecular weight and the hydrogen bond donating accepting ability, these things can be miscible in water. And what I mean by miscible is that you take water, the amine, you mix it, and you get one phase. There's not a phase split. And I'm not sure we'll get to it today, but say we have dimethylamine. Primary and secondary amines are kind of like alcohols, and the word I'm going to use is ambiphilic. Meaning they will behave differently under acidic or basic conditions. So this NH has a pK of about 35. So that it's a weak acid. Meaning to deprotonate it, you have to use a really strong base. But the presence of the lone pair also makes dimethylamine a base, which you can react it with acids. So the lone pair in the NH will do different things depending on what reaction medium you're in. And so there's, this is a really crappy drawing. I'm gonna draw a lobe here, and that lobe is the lone pair right there. So this is methylamine. So that lone pair can be an acceptor to an OH of water. This NH can be a donor to the lone pair on oxygen. So you have these two different interactions that help make it miscible with water. Questions?
So can we decide how we are going to use it as, can we fix how it's gonna be as an acceptor or donor when we are doing any reaction to it?
You really have to look at what it's reacting with. And again, that's how you need to, however you classify in your mind, are those reagents acidic or basic? Are they oxidants or reductants? And then that's going to determine how the amine reacts. So I think I only wrote one of these slides. So I'm talking about a primary amine on this slide. And so primary means it has the NH2 group. If it was secondary, it would just be NH. In tertiary, there would be no NH. As we'll see in the subsequent IRs, primary usually has a strong diagnostic, secondary not so much, and tertiary not at all. For mass spec, if you have an odd number of nitrogens, the parent mass is going to be odd. So that's a strong indicator. Like with ethers, proton and carbon, if you see signals in these heteroatom regions, coupled with other pieces of evidence, that's how you can clue into whether nitrogen is present or not. So we have butylamine. And this is a primary amine, so it has that NH2 group. And it's pretty subtle, but what you'll notice over here in region 1, it goes down, back up, and down. So the fact that there's like 2 of those is kind of indicative that the nitrogen is bearing 2 hydrogens. And if you remember what an alcohol looks like, it doesn't look like that. So it's just a visual clue. And if we extend that logic going from primary to secondary, we're removing 1 hydrogen, so it shouldn't have that double dip. And you see it's even less now. So now we have dibutylamine. So this only has the 1 NH, and that's this little baby blip there. And so I think the last one is just tributylamine. You're removing the NH completely. So tertiary amine, no NH group, so there's nothing there. So to me, that IR is not terribly diagnostic of anything. You'd have to get like mass spec information. So I recycled a slide from Organic 1. So this is the mass spec of aniline, and that number is super tiny. But basically this says 93. So again, since it's odd, so I always got to make sure I'm covering myself here. It's an odd number of nitrogens. I don't want to say it's 1 nitrogen. It can be 1, 3, 5, whatever. So mass spec is a really good diagnostic tool to determine the presence of nitrogen. Questions? So we got about 6 or 7 minutes left. So we'll land the plane nice and easy. Hopefully there's not another plane on the runway. So, did you see that video yesterday? Like, I don't know what's going on with planes nowadays, but maybe they've just been lying to us about aircraft safety all these years. So we'll end with why nitrogen is important, why it's a little bit more special than oxygen. So plants are organisms that produce nitrogen-containing compounds. These things are called natural products, and if they have nitrogen in them, they're called alkaloids. And, if we were alive, 120 years ago and we were doing chemistry, a lot of stuff was done with senses back then. So people would get a plant, and then they would taste the leaf of the plant and be like, this is bitter. And so it became known that a good observation was if you tasted something that was bitter, there was probably some nitrogen compound in there. And so a lot of these old-timey papers will say, bitter constituents of this maple tree or something. And so what I'm showing here is a skeleton called tropane. So that's a natural product in itself. And then you've all likely heard of a molecule called cocaine. And so what that is a substituted tropane skeleton. And you basically have 2 different type of esters. And so cocaine is, cocaine is known as a stimulant, right? So it's, is it legal anywhere? I don't think it's legal anywhere. You know, I don't have my Coca-Cola here, but, you know, apparently it used to be in Coca-Cola when people were more civilized with things, right? But my understanding is, even though it's a stimulant, it was used in dentistry as like one of the best analgesics you can get for like a toothache. People would just rub a little bit of cocaine on their tooth and like soothe the toothache. But nowadays, unfortunately, we don't have, you can't walk into CVS and ask for 5 grams of cocaine without the DEA showing up. So a lot of these natural products have analgesic indications, so that just means painkiller. And so I have morphine. So there's the morphine skeleton. And so I guess you see the flower there, that white flower? There's also this like pod. So I've never seen one of these in real life, but you know, I think it's bigger than like a golf ball or something. So that pod produces this latex, and basically it's scored with a razor, and that latex leaches out. And then from that, you can extract morphine. So morphine comes from Morpheus, which is like the god of sleep or something, right? So it's sort of the gold standard in painkillers. One of the issues with it is like addictive, right? So it does its job, but then your neurons get happy and they want more and more and more, and it's an addictive chemical. But it's not the strongest painkiller. And so what companies will do is functional group modifications. So based on that skeleton, you know, this alcohol has become an ether. This secondary alcohol has become a ketone. This alkene has been reduced, and that carbon has been oxidized. And so that's called OxyContin. And if you followed sort of the opioid epidemic in America, this company, Purdue, was known for pumping up sales of OxyContin illegally, basically through bribing doctors. And you know that pain scale, if you've ever been to the doctor and it's like, how's your pain level? And it has the faces. So they're the company that came up with that as a way to push more pills. This molecule here, it's buried in there, but it's naloxone, and it's sold as Narcan. So you can see the subtle differences between OxyContin and that. And this is an agonist or antagonist. It's one of those things, basically. This thing likes to bind to the receptor more than that. So once this is shot up through the nose spray, it kicks that out. But it doesn't have the addictive quality. So it helps in case of an overdose. It gets it out of there. And so that's shows you structurally how similar things can be, but very different indications. And with that, we'll end today. Have a good spring break, and then when we come back on that Monday, we'll learn about reactions.